We will continue our discussion of discrete probability distributions with an example. So we'll toss a coin 3 times, and the random variable will be the number of heads. Well, we'll start with creating our sample space. And just for to illustrate how we might do this, we can use a tree diagram. That's just one way to do it, but I want to show you how we could do that. So we'll use a tree diagram, and we'll represent our first toss here. Okay, and on the first toss we could get heads or tails. Okay, second toss, if we got heads, when we toss it the second time, we could get heads or tails. Or on the first toss, if we'd gotten tails, our second toss could be heads or tails. Okay, now the third toss. Well, if we tossed heads on the first, heads on the second, we could again get heads on the third, or on that third toss, tails. Likewise here, and here. So tree diagrams can help you visualize all the outcomes of a procedure, but you can see that it could get awfully tedious and complicated if I had a much more involved experiment. But this procedure is, works for this type of illustration. Okay, so now we want to find our sample space, and I can see that one possible outcome was heads, heads, heads. So I'm just going down the branches. I could have had heads, heads, and then tails. Alright, so I've exhausted all the heads, heads, the options there. So now heads, tails, heads, and heads, tails, tails. Okay, that's every possible combination if heads were thrown on the first toss. So now if tails is thrown on the first toss, I have tails, heads, heads, tails, heads, tails, 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 heads, and the last all tails. So again, this is a nice way, to create our sample space. Let's see if we can fix that real quick. Alright, sample space. Okay, now remember our random variable x, represents the number of successes. And what was a success? Remember, x was the number of heads and in general what we say is we're looking for our number of successes. That's in our general way of talking about this, whether we're looking for heads or the number of people or light bulbs or whatever we're interested in counting. Alright, so what are all the possibilities when we flip a coin 3 times? Let's make a table. Well, we might not get any heads. We might get 1. We might get 2. We might get 3. But that's it, right? Because we've only flipped the coin 3 times, we can't possibly get more than that. Let me change my color here. Alright, well, what's the probability of each of these values of the random variable? So this is I'm creating a probability distribution. Remember that definition. It's a formula or a table that represents or provides to us the probabilities for each outcome of a procedure. Okay? So I'm creating this table with probabilities for all my possible outcomes. These are all the possible outcomes if you flip a coin 3 times and you're counting the number of heads. Well, what's the probability that I get 0 heads? So let's look back at our sample space. there was only one case where we didn't get any heads, and that happened right here, correct? So there is one way for that to happen out of our 8 possible outcomes. So the probability that I don't get any heads is 1/8. Well, what's the probability we get 1? Let me change my color here. 1 head. There's 3, there's 2, there's 2. Here's 1. There's a 1, 2, there's a 1, and here's 1. So there are 3 ways out of 8 to get 1. My table's going to get a little tight here. Okay, how many ways to get 2? Here's a 2, here's a 2, 2 heads, 2 heads, 2 heads, and that's it. So 3 out of 8 for 2, and finally for 3, of course, there's just this one, 1 out of 8. So squeezing that in, 1 out of 8. Okay, let me pull that up a little bit. That's a little hard to read. See if I can fix that. Okay, this is for 3, it's 1 out of 8. Okay, so this was all the probabilities of our sample space. So we might recall, but let's reemphasize that and check that the sum, and we use this capital Greek letter sigma to represent sum, the sum of the probabilities of x in our sample space would be equal to, well, in our case, it's the probability of 0 heads plus the probability of 1 head plus the probability of 2 heads plus the probability of 3 heads. So that would be equal to 1/8 plus 3/8 plus 3/8 plus 1/8, which when we add those up, 1 plus 3 is 4, plus 3 is 7, plus 1 is 8 eighths, or 1. And we've said this before, the sum of the probabilities in the sample space should be equal to 1, with only difference being if we had done some rounding, if we had used decimals, carried it out several decimal places, but still had to do some rounding, that could have been 1.0001 or 0.9999, and we understand that that's just a rounding difference. But here in this case I used fractions and I got exactly 1. So that leads us to an important point here as far as the requirements of a probability distribution. So now that we've seen how we can create a probability distribution, let's talk about the requirements of a probability distribution. Okay, and one requirement is just what we've done here, that the sum of the probabilities has to be equal to 1. The sum of the probabilities of our sample space must equal 1. Okay, that's our first, let me mark that, that's number 1 in our requirements of our probability distribution. And the second one is, and we've also seen this, that all of the probabilities in our sample space lie between 0 and 1 inclusive. We don't have any probabilities greater than 1. We've already discussed that that wouldn't make any sense. And we don't have any probabilities less than 0. Recall that it's a ratio, the number of ways something can happen out of the total number of outcomes in the procedure, and obviously the numerator can never be larger than the denominator, so we won't ever get a number larger than 1, and it won't be negative, so we'll never get a number smaller than 0. Okay, these are very important requirements that you're expected to know, and will carry us through all of our discussions on probability distributions. Okay, so we can actually graph these probability distribution in a probability histogram. So let's do that. Okay, so we're going to create a probability histogram. And in a probability histogram, the horizontal axis are the random variable values. Let me make that note. Horizontal. These are the values of the random variable. And then on the vertical axis are our probabilities. For each one of these random variable values. Okay, so let's see what that would look like for our example of tossing a coin 3 times. Okay, so if the horizontal axis are values of the random variable, our values were 0 and 1 and 2 and 3. Okay, now we're going to construct bars. They're histogram bars, and they're in the shape of rectangles that we've seen before, and the width of the bars will be 1. So I'm going to make a note here. The width is 1. And the length is the probability, or the height of the bar, right? So they will vary. Okay, let me pick another color here. All right, for 0, we had, and so I guess let me get my scale on the vertical side. These are our probabilities. Just going to abbreviate probability, okay? So we had 1/8. Mark. Okay, and this will be 2/8. And 3/8. And we didn't have anything higher than that in our list of probabilities. So I'll just stop there. If I needed to, I could go further. Okay, for 0 heads, we said, well, there's only one way that could happen out of 8 possible outcomes. So that's 1/8. Okay, so my bar is a width of 1. Okay, for 1 head, 3/8. So the bars touch. Remember in histogram, the bars touch. There are no gaps between. Okay, 3/8. For 2 heads, the probability was also 3/8. Having a little trouble drawing a straight line today. And then for 3 heads, when you flip a coin 3 times, there was a 1/8 probability for that. Okay, so now we have a histogram. Now the area under these bars, this is a 2-dimensional area now. We've got rectangles. The area, if we sum up all these areas, that should be equal to 1. Because the sum of these represent our sample space, right? And if this is a distance of 1, then length times width for the 0 category here is, for our 0 count, is 1 times 1/8, or 1/8. So that area in there is 1/8. This area would be 1 times 3/8, or 3/8. And then the total area, well, in general, remember, area of rectangle equals length times width. So we could find the area of each one of these, and as I was saying, 1 times 1/8 is 1/8. 1 times 3/8 is 3/8. 1 times 3/8 is 3/8. And 1 times 1/8 is 1/8. So that's the area of each one of those rectangles, and therefore the sum of the areas, as we've already seen now, would be 1. And so the total area is equal to the total probability of the sample space. And what's that equal to? That's a constant. That is part of our requirement. That is 1, right? Okay, so we know the sum of the probabilities of the sample space must equal 1, and now we see that the sum of the area in the histogram must equal 1, because there is this correspondence between area and probability. There is a correspondence between area and probability. Very important concept here. Okay. So now what's all this for? I mean, we've got our probability distribution as a table. We've got our probability distribution as a histogram. Okay, we said it could be a table or a histogram or a formula. And we've got a table, we've got a histogram that's showing the probabilities, all possibilities of getting ahead on tossing a coin 3 times. So how is this useful? Well, because we might want to answer some questions about this procedure. So let's look at some questions we might want to be able to answer. So let's say, I'll just call this A. What's the probability that X is 2? Okay, so we can go to our histogram and look at 2. We can go to our table and look at 2, but we can see that the answer to that was 3/8. Okay, well, we might be interested in finding the probability that X is less than or equal to 2. What's the probability that we get less than or equal to 2 heads when we toss a coin 3 times? Another way to say this would be at most 2 heads. The most would be 2, but that means we could get 1, we could get 0, right? So let's see how we would say, let's write that out then. So at most 2 or less than or equal to means you want the probability of 2 or the probability of 1, or, see I'm saying or, look at this, I'm using addition, or the probability of 0. So we saw in our table before that 2 was 3/8, 1 was 3/8, and 0 was 1/8. So the probability would be the sum of these, or 7/8. Okay, well, you might be thinking, and if you are, good for you, that we could have done this another way. The probability that X is less than or equal to 2 could have been found through complements. Well, less than or equal to 2, as we said, that's, looking at our table, that's 2 or 1 or 0, but that's everything but 3. So a quick way to do this would be to say then that this is 1 minus the probability of 3, because that's the only thing we're not counting here. So either you get 3 or you get 2 or less, right? Those two are complements of each other. So that would be 1 minus 1/8, and here's a quick way to get that 7/8. Okay, more than one way to do that. Let's look at one more question we might could answer from this very simple probability distribution and this simple procedure. The probability that X is greater than or equal to 1. Now a wording for that would be at least 1, right? Because the lowest it could be is 1. At least 1. So let's write that. Probability of at least 1. Well, what numbers in our list of possibilities are at least 1? Well, 1 is at least 1, but so is 2. 2 is at least 1. If you have at least $1, you've got $2. Yes, you've got at least $1. Plus 3 is at least 1. And I can't go any further because we only tossed the coin 3 times, right? So notice the only thing that's not missing there, that's not listed there. We could use complements here too. That would be the same as 1 minus the probability. So what's the only outcome not listed? 0. So we might note that that's another way to say that is 1 minus the probability of none. We'll see this again, but the probability of at least 1. It doesn't matter if we'd flipped the coin 50 times, right? The only thing not included in our list would be 0, because we'd have 1 plus 2 plus 3 all the way to 50, and the only thing missing when you're looking for at least 1 is 0. So you can always use this complement. So the probability of at least 1 is equal to 1 minus the probability of none. Handy thing to remember, especially what if this had been 50 flips? I'd be writing this out, plus 4, plus 5, plus 6. I'd have a lot of work if I didn't understand this real quick, easy way to use complements. Okay, so let's get the answer to this. 1 minus, and what was the probability of none? 1/8. So we get 7/8 for this answer. Okay, so that's a very simple example of a discrete probability distribution.